What if your AI could instantly pull up relevant memories from past conversations, like a user's favorite foods, just by analyzing their current message? We'll see how to implement semantic search in LangGraph to retrieve user-specific memories across threads. The pattern uses a BaseStore to namespace memories by user ID, then performs context-aware lookups to surface the most relevant information for the model's next response.
Def call model state, messages state config, runnable config asterisk store, BaseStore. Hash get the user id from the config. User id config configurable, user ID. Hash namespace the memory. Namespace equals user id, memories. Hash search based on the most recent message. Memories equals store search. Namespace. Query equals state messages -1. Content. Limit equals 3. Info equals \n. Join D value memory for D in memories. Hash use memories in the model call.
This demonstrates the persistent context pattern for stateful AI workflows, where user-specific data persists across multiple interactions while maintaining isolation between sessions. The concept revolves around separating ephemeral conversation state managed by threads from durable user memories stored in a namespace-scoped store, enabling both short-term dialogue continuity and long-term personalization. What makes this distinctive is the dual-layer persistence. Checkpointers handle thread-local state for individual conversations, while the store maintains cross-thread memories tied to user identity. The pattern works by establishing two orthogonal persistence mechanisms. Threads capture the linear progression of a single conversation, with checkpoints preserving state at each step, while the store provides semantic, user-scoped memory that survives across threads. When the model processes a message, it dynamically retrieves relevant memories via semantic search, querying the store using the current message content, then incorporates these memories into its response. This creates a separation where conversation history lives in threads, but user knowledge persists independently, allowing the system to maintain context even when starting new conversations. This approach solves the problem of context fragmentation in multi-session systems, where users expect continuity but technical constraints often reset state between interactions. It's particularly valuable for assistant applications where you need to remember user preferences, past interactions, or domain-specific knowledge across multiple chat sessions. The trade-off is increased complexity in managing two persistence layers. But the benefit is a system that feels genuinely stateful to end users while maintaining clean architectural boundaries between session data and user data. Let's break it down line by line.
Def call model state, messages state config, runnable config asterisk store, BaseStore.
This defines the core function that handles AI model calls, taking 3 parameters: the current message state, runtime configuration, and a persistent store for memory operations. The keyword-only store parameter enforces explicit dependency injection, preventing accidental misuse of default values.
Hash get the user id from the config. User id config configurable, user ID.
Extracts the user id from the configurable section of the runnable config. This identifies which user's memory to query, enabling personalized memory retrieval in multi-user systems.
Hash namespace the memory. Namespace equals user id, memories.
Creates a scoped namespace for memory storage, using the user id as a unique identifier. This prevents memory collisions between users by isolating each user's memories in their own namespace, while the memories string categorizes the data type.
Hash search based on the most recent message. Memories equals store search.
This initiates a semantic search against the vector store, using the most recent user message as the query. The store search method retrieves contextually relevant memories that will augment the model's response, implementing a simple RAG pattern.
Namespace.
This is the namespace key for memory isolation. By combining userid and the string memories, it creates a unique storage scope per user, preventing data leakage between users.
Query equals state messages -1. Content.
Extracts the latest user message content as the search query. This targets the most recent input to find relevant memories, ensuring contextual continuity in the conversation.
Limit equals 3.
Limits the memory search to 3 most relevant results. Controls response precision by preventing information overload while maintaining contextual relevance.
Info equals \n. Join D value memory for D in memories.
This transforms the memory search results into a newline separated string. It extracts each memory's content from the value memory, field, and joins them with newlines, creating a clean input format for the model. The pattern efficiently converts structured data into a simple text representation. LangGraph memory integration pattern. The call model function demonstrates how to persist and retrieve user-specific memories using a key-value store, with namespacing ensuring isolation between users while maintaining continuity across threads. The userid in the configurable object determines memory scope, so changing it creates a completely separate memory space, even with identical thread IDs. This pattern enables stateful conversations that persist beyond individual sessions, forming the foundation for personalized AI interactions.
The userid that changes nothing carries all memories.